My name is Brian Gonsalves, and I'm a second year computer science student. And today, in continuation with the Technique series, I will be trying to explain time and space complexity. So, let's get started of why do we have to learn time and space complexity. So, time and space complexity is vital in a lot of things and a lot of systems around the world. To give a brief understanding is, you ever look at your phone and say, hey, why is this application taking so long? Or, hey, why is this app taking so much more space compared to its competitor apps? It has a lot of factors, but a lot of it has to do with the time and space complexity. Second, we talk about the industrial sense. This is very crucial in writing efficient code because efficiency means, time and safe and cost reduction. So, very important. And why, when you go to your technical interview and you see often they ask you, hey, what is the time complexity of this code? Or, hey, can you write a code for this problem statement that satisfies big O of n notation or big O of n squared notation? So, these all are very, very important. So, I'll try giving a brief overview of what are these things and so that you will understand what time and space complexity is. So let's get started. So first I will give an index of what I will cover and the contents of this. So firstly, I will cover the definitions of both time and space complexity. So what does time and space complexity mean? It's important in the algorithm design. When you design an algorithm, how you balance time and space complexity depending on what is the code for. It's important that you don't concentrate just on time complexity, writing efficient code for your time complexity, but also worry about the space complexity because you need to balance those both. So if so at the end of the day, you need to write efficient algorithms. So that's the goal of it all. Efficient algorithms for industries, and that's the standard nowadays. So it's important that you understand this because it's every day and it's vital. So let's get started. So what is time complexity in a single line? So I would say the definition of time complexity is the amount of time an algorithm takes to complete. In other words, you can say also that it is the rate at which the time taken decreases in respect to the input size. And it is denoted in big O of n notation. So big O of n notation is what we consider the worst case scenario notation. You have an average case, you have a best case. These are denoted by omega and theta. But we have to talk about worst case scenario because when we do test cases, you always got to take the baseline to figure out the rest, So baseline being the worst case in any test case that you do. So examples of which, how they donated is big O of 1, big O of log n, big O of n, big O of n squared. So many notations are there, but you get the point of how they're written. So that's about time complexity. And now you may ask how you get that definition, how you get big O of n notation. So I will now explain that when I jump on the whiteboard. Okay, so first let's talk about what is time complexity. So time complexity can be understood in where you have, let's say you have a piece of code, yeah. Now this piece of code, when you go for an interview, technical interview, they're not going to pass this through a machine and say, hey, this is the time taken and okay, what is the standard machine? They're not going to do all that. Rather, they'll simply ask what is the time complexity, and B, what is the space complexity. So this is what's going to be asked. So what is time complexity? Now first you would say, hey, would it be the time taken? Well, let's try to break that down. Let's say you have this piece of code and you pass it through a computer, sorry, and it runs in 2 seconds. It maybe runs in the next time it runs in 3 seconds. The next time it runs in 5 seconds. Is these values fixed? No, these are fluctuating values. So I cannot equate time complexity with time taken. I can't do this because you can see that the value will always change, and depending on the computer you use, it'll have varying values. So rather, you wouldn't apply this. You would not say that it is the time taken. Okay, so if it's not that, let's say you have two computers. Let's say you pass this piece of code into two computers. Let's say you pass it through a Windows Vista, the old one, 2002. Let's say you pass it through this one, and let's say you pass it through the latest 2023 M2 MacBook Air. And then I ask you quickly, hey, run the same piece of code and tell me which one will produce the fastest speed. You could say that this one will take 1 second, this one will take maybe 2 seconds or even more. And then would you say that this, then you would say, hey, this is the faster one. So this is not the time complexity. This is because you have different varying values. So what is the actual definition? The actual definition that we give, it is that it is the rate at which the time taken decreases with respect to the input size. So let's try to understand this through a graph. So we plotted here, we have the old Windows that we mentioned, and we have the new MacBook, the 2023 MacBook M2. So in these two, we can denote it using a graph, and since the definition specifies input size, we'll denote on one side the time taken, so this will be time, and this would be the input size. So you'd have 10 here, let's see, you have 20, 30, 40, and 50. Here you have the time in seconds, 1, 2, 3, 4, 5, 6. You may imply that, hey, for 10 input size you get a value of 2, maybe for 20 you get a value of 4 as number of seconds. You increase it all the way to 40, you're getting maybe, let's say, 6. Okay, likewise we repeat the same thing for the new MacBook. You have 1, 2, 3, 4, 5, and 6. Similarly, the time taken, the input size would vary, and here you would draw a slightly, you would have a smaller angle. So I would say, let's say we put the values as 1 second for every input size, so 2, and 30 would be 3. So let's plot this. Okay, now you can say that here this angle, call it theta, can be denoted as, like I mentioned, the rate of increase in respect to the input size. So that's basically what it's saying, that if the input size varies, then the time complexity will vary. So depending on the input size, you will have a varying rate of time taken. So rather than implying that time complexity is equal to time taken, we have to state that the rate at which it increases or decreases with respect to the input size. Okay, so the next part to this is how now do we denote this time complexity that we mentioned. So what we use is we use a big O notation. We use big O notation, which looks something like a big O with brackets, and these brackets signify the time taken. So let's take an example here. Let's write a piece of code in, let's say, C++. So let's say for I is equal to 0, where I is less than 5, I plus plus. And then in this we write print out, let's say print out the word time complexity. Okay, so considering this now, what would you say the time complexity would be? So you can clearly see here that we have 5 iterations through this. So would you say that, okay, so you have 5 iterations, but let's see how many operations it goes through. So what does it go through? So it goes, checks, it initiates the value. Okay, done. It checks condition, prints the statement, increments. Checks condition, prints the statement, increments. Check the statement. It continues until this condition no longer holds. So you can say that it goes in a loop of 3, no? So this condition checks this, increments, and prints. So you can say 5 into 3, no? So you can say what, 15? So can you write O big O of 15? Yeah, you can write big O of 15. So what rules do we apply when we do this kind of denoting? There are 3 important rules that you must always consider for time complexity. These are the golden rules. First, time complexity always considers the worst case. B, you would have to avoid using constants. And C, you have to avoid also lower values. So the first one is considering the worst case scenario. Like I mentioned, big O of n notation takes consideration the low case, the worst case scenario. Why? Let's say this value is now changed into n, where we don't know the value. We don't know the value of n. So can we say that big O of n times 3? Yeah, we can say n times 3, no? Because we know 3 notations. So it considers the worst case scenario. So let's take another example here. Let's do an if condition. Let's say if x is equal to 1, if x is equal to 1, print hello. If else if x is equal to so three statements here: if one, if two, if three, else we print done. So considering the worst case, so you have your best case, your average case, and your worst case, yeah? So if you consider the best case would be the first one, no? So x, let's hypothetically x actually equals to 1. So in that case, you don't have to go through the remaining conditions. You can say that it'll print hello world, hello, and you're done here. So that is your best case. Your worst case is it's not 1, it's not 2, it's not 3. That means it has to go to else. So how many times is it going to? 1, 2, 3, 4 operations to get through to this last one. So this one will print this in the last iteration. So that is your worst case. An average would obviously imply your best case and your worst case, and simply finding the median between those two. So that is to give an understanding of the worst case scenario. We always consider the worst case because in a system, you always want to think about what can be the worst case in order to prepare yourself correctly. What I mean by that is, hypothetically, let's say you're running a e-commerce site and you launch a new product. You're not going to think the best case being, if you're solely responsible for the operation, the running of the site, you're not going to think the best case. Okay, I'm just going to have maybe, let's say, 5-10 people visit the site, so there's not going to be any issue. Rather, you're going to think, okay, worst case, I have 500,000 people visit the site. How can I ensure that, that is the time complexity? That is the worst case. So what would be the time complexity? So always take the big O notation. So that's rule number 1. Next is avoiding constants. What do we mean by avoiding constants? Avoiding constants in the sense that, let's say you have a notation that looks something like this: 4n squared, let's say 8n squared plus 6n plus 8. So what would you say here in this case? I would say that, you have these values, that are significantly larger than this 8. This 8 won't make a difference at all. Let's say, hypothetically, let's say n is equal to 10 to the power of 6 or 10 to the power of 7, let's say a million. If you have 10 to the power of 7 squared plus 6, plus 6 million plus 8, you think this is going to make any difference to this value? No, it's not going to make any difference to this valuation right here. Rather, this can be simply discarded, because you're not going to make a drop in the bucket if you're adding, for example, 1 to an equivalent 10,000. So that's why we, in the rules of time complexity, we do not consider constants. We also don't consider lower values. What I mean by this, let's take for example, you do let's take for example in this case right here. Oh, I forgot to square this value right here. So let's take in this case, for example, you had 10 to the power of 14 plus 6 6 to the power of 10 squared 11 plus 8. So 10 to the power of 14 is significantly greater than 6 million, or 10 to the power of 7. You have 7 zeros. So you can see, if you think about proportional wise, you can say that every one value you're adding of this 7, you're adding it to 7 zeros, of this. So it's not really going to impact this value that much in terms of time complexity. So we don't really consider the lowercase values. We take the highest value here. So this would be n squared O. Okay, so those are the rules that you have to consider when you are trying to denote what is time complexity. So very crucial, very important, these 3 rules. Okay, so now since you understand what big O notation is, let's take this question example. I'll give you a couple of seconds to quickly pause the video and try to figure out what is the time complexity of this. Okay, new question. Now you tell me what would be the time complexity here. Pause it and tell me it now. Okay, so to find the big O of n in this case, it's very similar to the previous problem, but instead of putting here the value of n, we have denoted it as I. So can we say that firstly, when I is equal to 0, j will be equal to 0? Yeah, only because we only have I. Then when we have I is equal to 1, j can be equal to 0 and 1. Yeah, and when I is equal to 2, it can be equal to 0, 1 and 2, and we continuously go through those all until I is equal to n minus 1. So you can say j is equal to until n minus 1. Yeah, so then can we say that rather than writing 1 plus 2 plus 3 plus 4 until n, can we write that instead n, which is the number of times n plus 1, because that is the second iteration that we do, divide that by 2. Can we say it like this? So what would this be? This would be simply n upon 2 plus n squared upon 2. If we multiply this across, we get n squared plus 1 divided by 2. We get n squared divided by 2 plus n divided by 2, which can finally be written as O of n squared divided by 2. Why? Because we do not consider this constant value right here, the lower value, sorry, because this is obviously bigger and does not have the impact on it like n squared has. So we just take the larger value, we avoid the lower values, and we come to the final conclusion that n squared upon 2 is the time complexity of this piece of code. Time complexity, we can understand what the factors are that influence time complexity. So firstly, it would definitely be the input size. It's in the definition itself. When I mentioned that the time taken decreases in respect to the input size, so increasing or decreasing the input size will have an impact on the algorithm's efficiency. Second would be looping and recursion. So the number of loops that you have, the number of times the code recurses by itself will have impact on how much time it takes, or the time complexity. And finally, identifying the big O of n notation, always the worst case scenario, rather than considering the best case or average case, because that would be ideal, but it's not always the case. So taking the bottom line, the baseline, the worst case scenario would be the way to go. So identifying the worst case scenario would be the correct way to go. You can think of it like a binary search. A binary search works when you're searching for a value in, let's say, 1500 integers. You may get that value in the first attempt of doing your search. That's the best case. Average case maybe after 50, 100, 200 attempts. Worst case is you go all the way to the last, you go all the way to 1500 searches and then you get the value. So that's the worst case. And so calculating the worst case would be the way to go to figure out the rest. So big O of N notation is the standard that is used across the world. So now, since we got an understanding of time complexity, we can move into space complexity. So what is space complexity? The definition of space complexity is the amount of space, the amount of memory that an algorithm uses. So you can put it in two parts. You can say that it is the auxiliary space and it is the input space. The auxiliary space is the space required in order to solve the problem, and the input space is the space required in order to store the problem. So I will explain that when I go to the whiteboard, but yeah, it's two parts. It's the algorithm, it's the auxiliary space plus the input space. It is also denoted in big O of N notation because we consider the worst case scenario, and it follows the same structure, so I'm not going to repeat myself. Big O of 1, etc., etc. So now I'll jump into the whiteboard and explain to you. Okay, so the second part is the space complexity. Now, space complexity is a bit easier to understand. I mean, it's simply the amount of space that is going to be taken up by your program. So it's essentially the memory space, and it is also denoted by big O N notation. We use a similar because we take the worst case scenario again. You can divide the memory space into two. You have the auxiliary space and you have your input space. So auxiliary space would be the space taken to solve the problem, and input space would be the space required to store the problem. So let's take, for example, we have two variables A and B. These contain some value, let's say 5 and 10. Okay, and so these are the variables. Yeah, you're going to store the problem in B, and you input it in, let's say you put it in B, these to solve it. So this would be considered as the auxiliary space, because this is what stores what you're using to solve the problem, and A and B would be considered the input space. So these would be considered the input space because they are what's going to be storing the problem. Another example would be if you declare a variable, let's say A, an array A of n. Okay, so what would be the space complexity here? It would simply be O of n, because we take the size of the array. It's as simple as that. Okay, so another thing I got to explain is that if you have your variable A, yeah, and you have your variable B, if I give you a program, you would and I say, try to reduce the space. To impress the interviewer, you may simply just put it in the same variable. You may not add another variable. You may do a plus b. While yes, this is correct, and yes, this will save space, the issue with this is as follows, and why when an interviewer sees this, they'll usually cancel this out. They'll say, hey, this is wrong, or this is not acceptable. Why? And because in the industrial sense, why? Because in the industrial sense, what you have is, sorry, so to save space, you're going to store it in the value b. Yeah, well, this is still correct, and it is going to save you space and hence help space complexity, although the interviewer will say that this is not acceptable in our industry. Why is that? Because if you think of it as a software engineer, a software developer, the main issues lie with the fact that you take it into the large scale, in these companies and organizations. If you're manipulating, the variables that store the problem, you're going to manipulate a lot of issues and create a lot of issues with other, data sets and a lot of other processes that take place. So they do not like seeing developers have a habit of um, reusing variables, essentially, which already consists of the problem. So do not modify the data set, rather they create a new variable, even though if it takes O of n, 2n, for example, adding an extra variable, that is still fine, rather than simply trying to do O of n and manipulating the data set itself. So a major rule here is never do anything, never manipulate the data set of the input, no matter. So that's the major rule. So those are the simple understandings of what space complexity is. Okay, so now you know what time and space complexity is. And so just to brief over it, the factors, of course, the data structures will impact the amount of memory that is used. If you use something, let's say, for example, use a linked list or hashing, it will definitely improve, your time complexity, but it'll have a massive overhead on the memory that you use. So compared to something like a one-dimensional matrix, so identifying the data structure that you use is crucial for space complexity. Recursion calls, the amount of recursions that you do affects the memory stack usage. Dynamic memory allocation. So as you know, you can allocate memory dynamically or statically. Static would be, before the code, before you run the program, it's already stored, wastes a lot of memory. So you should ideally have dynamic memory allocation to not waste space. So let's try to compare it, but I wouldn't say compare. I would say, you've got to balance it. Why? You can have a code which is too time, optimal and not too space optimal. As I mentioned clearly with the phone example, you want something where the application can be both time and space optimal. So that's important. So balancing those two, because you don't want this app that is too slow, at the same time you don't want an app that takes too much space. So finding the right balance. So the trade-off, like I mentioned, choosing the right algorithm when it comes to the data structure. You need a fast code, but you don't want something too slow. So choosing, whether it be hashing or whether it be an array, or whatever it may be. So figuring out linked list, that all will be there. When to prioritize time and space. So you can always have a balanced, equal 50-50 on time and space complexity. You've got to prioritize depending on what type of application it is. If it's something to do, where time is very important, real life applications in medical equipment, that is important to, prioritize time compared to space. So figuring out what is more important and then prioritizing that. Practical implications, I covered it basically throughout. There's numerous occasions everywhere in the world. You need to optimize time and space, because like I mentioned, in industrial sense, you have costs and you have time reductions that need to be considered. So lots of things. You're talking about big data analytics, you're talking about large number of data sets, very crucial in getting the time complexity and space complexity in play. Tips for algorithm design. When you're designing the algorithm, it's pretty much all we have covered. Understanding the problem, whether you're prioritizing space or time depending on what application it may be, choosing the correct ID structures based on that, whether it be linked list, whether it be hashing, whether it be simple arrays. So understanding that, optimize your loops and recursion so that you don't have too many. At the same time, you need to make sure that the code runs, so having optimal number of loops and recursion. And obviously keep an eye on your memory usage. You don't want an app that takes too much space. So that would be tips for designing the algorithm. I won't delve too much in how to design it, because that's a separate topic in of itself. So okay, so let's conclude off with a recap of everything so far. So these all I've pretty much explained. So time complexity is the rate at which the time taken decreases in respect to the input size. Space complexity is the amount of memory that is used for the application. There's, like I mentioned, two parts of it: the auxiliary space, the space that is used in order to solve the problem, and the user space or the input space is in order to store the problem itself. So the importance in the algorithmic design, when you design an algorithm, what to consider, what not to consider. I've covered that. What data structures not to consider, what it is to consider, how to prioritize depending on what type of application it is. And this is a field which is continuously continuously updating itself, with a lot of new data structures, and any problem set can be solved in many different ways. So every time you have a new rendition to that problem and how to solve it. So this is something that you've got to work on and practice with, especially when you do your technical interviews. So whether it be LeetCode, whether it be HackerRank, these are great ways in order to test your ability in how to optimize space and time complexity. In a lot of problem questions, they'll ask you, hey, write a code in big O of n notation and big O of n square notation. So how to do that is very important. So I would say do that. And yeah, thank you.